We've seen over the last couple of days 3 types of standing waves. Standing waves produced in strings. A string that was attached at both ends would produce a first harmonic that would look like this. Notice there's a node at both ends and an antinode in the middle. Constructive interference in the middle, destructive interference at the end. Now, the other situations we saw were in air columns. Air columns like this one, which is called a closed air column, like a water bottle, a clarinet, something that's closed at one end but yet open at the other end, that can produce a standing wave as well. A little bit harder to visualize because we can't physically see the air vibrating in standing waves like we can the string. But in the end, there's still a standing wave. Looks a little bit different though, because we have to have a node at the closed end and an antinode at the open end. Finally, the other standing wave that we can have is produced in an open air column. An open air column is like a pipe that is open at both ends. Remember the rule. We have to have an antinode at an open end and an antinode at the other open end. So the first standing wave that we would see would look something like this. Now, if we define the length of all of these as L, then we would say the length of this one is what in terms of lambda? What's it going to be? It's going to be a half of a wave. So we're going to say L is equal to 1/2 lambda, or we're going to say lambda is equal to 2 times L. For this one, we're going to say L is equal to, how much of a wave do we have there? Yeah, that's going to be 1/4 of a wave. So we're going to say lambda is equal to 4 times L. And finally, the last one, we would say L is equal to, we're going from crest down to the bottom of a trough. L would be equal to a half of a wave again. So we're going to say L is equal to 1/2 lambda, or lambda is equal to 2 times L. Now, we take our wave equation, V is equal to F times lambda, rearrange it, we get F is equal to V over lambda. In all 3 cases, F is equal to V over lambda. F is always equal to V over lambda. But we're going to sub in for lambda 2L in this case. So we end up getting F is equal to V over 2 times L. In this case, we're going to sub in 4L for the value of lambda. So we get F is equal to V over 4L. And in this case, we're going to sub in 2L again. So we end up getting F is equal to V over 2L. What do we call this frequency right here? F is equal to V over 2L for a guitar string or anything else that's attached at both ends. It's called the first harmonic. This is the first resonant frequency of a string that's attached at both ends. We call it the first harmonic or the fundamental. What do we call this one? F is equal to V over 4L. It's also the first harmonic, but it's the first harmonic for the water bottle or the clarinet or the situation where we have one open end and one closed end with air vibrating between those two ends. The third one is also called the first harmonic, but again, this one is a little bit different. This is the first harmonic when we have something like a pipe with air vibrating back and forth between the two open ends. Now, if you want to find the next harmonic, the next resonant frequency in all 3 of these cases, what do? Well, we got 2 options. A, we can derive the equation for the next harmonic by drawing the diagram and going through the process that we just went through for our new diagram. Or what I recommend you do is what? Sorry? We can times this one by 2 to get the second harmonic. We'll call this the first harmonic, times this by 2 to get the second harmonic, times it by 3 to get the third harmonic, and so on, and so on, and so on. We'll do exactly the same thing over here. We're going to say this is F1. The second harmonic is 2 times the value of F1. The third harmonic is 3 times the value of F1, and so on, and so on, and so on. What about the middle one? What's the next harmonic for the middle one? Yeah, the next harmonic is the third harmonic. There is no even numbered harmonics. So we're going to say this one's still F1, but F3 will be equal to 3F1, and F5 will be equal to 5F1. There is no F2, there is no F4. All right? So as you're working on questions like you were on your worksheet last night and during class yesterday, remember that we always want to go through the first harmonic. That is, unless you're going to derive the equation for the third or the fourth or the fifth harmonic, then we always want to go through the first harmonic. If you've got the first harmonic, that's great. Use the equation for the first harmonic. Okay, if you don't have the first harmonic, if you're given the value of the third harmonic, then get the value of the first by dividing by 3. If you're looking for the value of the fourth harmonic, then go through the first harmonic using the equation for the first harmonic. Get the frequency and then simply multiply it by 4. Okay, let's take a look at question number 3 from our worksheet that we had for homework last night. It says, on the 3 on the second side says, the temperature of the air inside a particular open air column is 24 degrees Celsius. If the air column is 40 centimeters long, determine the frequency of the first 3 harmonics heard. This is an open air column. That means it's open at both ends. And if it's open at both ends, we know that there is a first harmonic, a second harmonic, and a third harmonic. We don't skip the even number harmonics for an open air column. We only skip them for a closed air column. So that's good. Okay, we don't need to worry about skipping the second harmonic and the fourth harmonic. We know the temperature of the air is 24 degrees Celsius. How's that going to help me out? Yeah, we can get the speed of sound there by saying 331 plus 0.6 times the temperature. 40 centimeters long, we want to find the frequency of the first 3 harmonics. So let's do that. Let's do that question here now. The temperature is 24 degrees Celsius. The length of the air column is 40 centimeters or 0.40 meters. And we'll find the frequency. Let's get the frequency of the first harmonic, and then we'll deal with the second and the third harmonic. Those are pretty easy once we get the first harmonic, right? This is an open air column. We're going to derive the equation, even though we just did a couple minutes ago. We'll derive it again here. This is what the first harmonic will look like. And we know that the length of that air column would be a half of a wave. So we're going to say L is equal to 1/2 lambda, or lambda is equal to 2 times L. Then we're going to say F is equal to V over lambda, but lambda is 2 times L. So it becomes V over 2 times L. There's my equation. Now I'm going to say F is equal to, I got to find V, I guess. Let's find V by saying 331 plus 0.6 times the temperature. This works for the speed of sound in air, not in string or in water or anything else, just in air. But that's what we're in right now, so we can do that. 331 plus 0.6 times the temperature of 20 degrees Celsius. No, sorry, 24 degrees Celsius gives me what as a speed there? 345.4 meters per second. All right, now let's take that value and sub it in over here. 345.4 meters per second divided by 2 times the length of 0.40 meters gives us a fundamental or first harmonic of 430. I got 432 as a rounded number. What's the unrounded number there? 431.75, which we're going to round to 432 hertz. That's the frequency of the first harmonic. Now, what's the easiest way? Not the only way, but what's the easiest way of getting the second harmonic? Just multiply by 2. Good. 431.75 times 2 is 864 hertz to 3 digits. And then 431.75 times 3 for the third harmonic is to 3 significant digits. Should be 1.30 actually, times 10 to the 3. All right, and the other question that we wanted to go over here was question number 11. So let's scroll down there. It says the length of a particular closed air column is 60 centimeters and the frequency of the third harmonic is 432. What's the speed of the sound in the air column? This is a closed air column. What do we know about a closed air column versus an open air column? There's a couple of things that I can think of that are different. What's one of them? Yes. Well, in an open air column, there's actually one node as well. It's in the middle. In the closed air column, the one note is at the end for the first harmonic, right? But that gives us, um, because the shape of that first harmonic is different, that first standing wave is different, that gives us a different resonant frequency. So it's a different equation for the first harmonic. We know that the equation for an open air column ends up being V over 2L. For a closed air column, it ends up being V over 4L. What else is different about the closed air column? This is probably the bigger thing to remember, to be honest. For a closed air column, there is no even numbered harmonics. There's no second harmonic or fourth harmonic. I'm not sure that that's going to be relevant to this question, but it's something that we always want to be conscious of. All right, so the closed air column is 60 centimeters long. The frequency of the third harmonic is 432. We want to find the speed of sound. The length was 60 centimeters. We're going to make that meters, 0.60 meters. Should be 0.600 meters. The frequency of the third harmonic, and be careful with this, right? Don't just write down F. The frequency of the third harmonic, F3, is 432 hertz. We want to find the speed. So what do we always want to do? Always go through the first harmonic. So we're going to take that 432 and get the first harmonic from that. It's going to be 432 divided by 3. And when I do that, wait a second. I just realized I made a mistake here. The wording of the question, let's go back to the wording of this question. The length of the air column is 60 centimeters, and it doesn't say the frequency of the third harmonic. It says the frequency of the third harmonic heard. What's the third one that's heard? Not the third harmonic, it's the fifth harmonic, right? We hear the first one, the third one, and the fifth one. So be careful with that one. Okay, be careful with that. Okay, I missed that, and if I missed that, then it would be really easy for you to miss that. We're not going to call that F3, we're going to call that F5. So that means if we're finding the frequency of the first harmonic, we're not going to divide it by 3, we're going to divide it by 5. And when we do that, we should get 86.4 hertz. Now I've got the frequency of the first harmonic, which is exactly what I want, because we always want to go through that first harmonic. Now I'm going to derive the equation. Here's my air column, and my first harmonic is going to look like this, with a node at the fixed end, or the closed end, and an antinode at the other end. We're going to say L is equal to 1/4 lambda, or lambda is equal to 4 times L. F is equal to V over lambda, or F is equal to V over 4 times L. Solving for V here, take the 4L up by multiplying, 4 times L times F. And the frequency that I want here, because I'm deriving the equation for the first harmonic, would be the frequency of the first harmonic, 86.4 hertz. Do that, it works out to be 207 meters per second. How many people did it more or less this way, except divided by 3 instead of dividing by 5? So lots of you did exactly the same thing as I did there, the same mistake as I made there, right? Be careful, right? Be careful of the wording of that. If you happen to see something like that on a test, and you're unclear what I mean by that, the frequency of the third harmonic heard, like you want to clarify, okay, is that the third harmonic, or is that the third possibility of a harmonic? Then ask. Okay, I'll help you clarify that. I'm not going to tell you, oh, you got to divide by 5 instead of divide by 3, but I'll clarify a little bit about what we mean by that. Okay? Does that make sense now? All right, our last topic of the unit, our last topic of the year. We just watched a video from the Big Bang Theory where Sheldon defined the Doppler effect very, very well. He defined it as the apparent change in frequency, not the real change in frequency, because frequency doesn't really change. Once a sound has been made, the frequency always remains the same. But the apparent change in frequency, the frequency appears to change due to the relative motion of the source of the wave and the observer. Now, usually when we talk about the Doppler effect, we're talking about sound, but it doesn't have to be. It happens with light as well. Have you ever heard of a red shift or a blue shift in the context of astronomy? Has anybody ever heard of that? No? Light from distant stars or distant objects in space can appear to become closer to blue or closer to red than it really is due to the motion of that star relative to us. Again, the apparent change in frequency due to the source and the observer. Okay, let me, before I give you an equation, draw a little picture that's going to help you to understand a little bit why this happens. Why, as the fire truck in the other video that I showed you just a second ago, appeared to have a higher frequency as it was coming towards us and a lower frequency than it really was as it was going away from us. Let's say that this is my source. Okay, this produces the sound, or this produces whatever wave it is that we've got, sound, light, whatever, water waves, whatever. Okay, this is my source. We know that waves will go out in all directions from that, spherically from that. Now we're drawing it in 2 dimensions, but we know that it's actually going to go out in 3 dimensions. We're going to represent it in 2 dimensions as a circle right here. Now remember, this source is moving. Let's say it's moving to the right. So by the time the wave gets to that point, by the time the wave is this big, the source is no longer actually in that position. The source is actually over here. Does that make sense? Now let's fast forward a couple more seconds in the future. A couple more seconds in the future, this wave that was at this position is now going to be bigger. This wave ends up being right here, right? Let's erase the wave that we just had because that wave is further out now. But the source is also further to the right. So the source is no longer in that position. The source is in this position. And the wave that the source made is going to look like this. But the source is actually closer to the edge of that wave because it's still moving. So as the source moves and the waves that it produces emanate from the point at which they were made, right? This blue wave was made at this point right here. This red wave was made at this point right here. But the source is now at this point right here. If you happen to be observing this, standing right here, what do you encounter? Well, you encounter the leading edge of these waves. So instead of having the waves as they're supposed to be, crest of a wave, crest of a wave, crest of a wave, you actually encounter them quite a bit quicker, right? So it appears crest, crest, crest. But if you happen to be standing over here and this source is going away from you, what do you perceive now? Well, the waves are more spread apart. So it appears to be a lower frequency. As it's coming towards you, they're closer together. It appears to be higher frequency. As they're going away from you, the waves are more spread apart, and it appears to be a lower frequency. Does that make sense? All right, let's go back to the equation now. This is, we saved the best for last. Last equation that we learned this year, it's a gooder. FD is equal to VW over VW plus or minus VS times FS. Let me tell you what each of these variables mean first, and then we'll describe this whole plus or minus thing, what that means. FD is the Doppler frequency, or Doppler frequency would be, another name for the Doppler frequency would be the apparent frequency. This is what we would perceive as the frequency, not the real frequency, but what we perceive as the frequency. It's the apparent frequency that's due to the relative motion of the source and the observer. And of course, that's going to be measured in hertz. Fs is the actual frequency, or the frequency of the source. That's why it's called Fs, frequency of the source, or the actual frequency. And of course, that's going to be measured in hertz as well. What do you think Vs is? Vs is a speed, of course. Now, be careful here, okay? A lot of people see it, look at this, and look at the subscript there, Vs, and think, oh, that's going to be the speed of the sound. It's not the speed of the sound, because it's not necessarily sound that is the wave that we're dealing with. Usually it is, but not always. Vs is not the speed of sound at all. What's it going to be, Alex? Yeah, it's the speed of the source. So in the video that we watched, well, the videos that we watched, first one would be the speed of the van, how fast the van was coming towards us, because it was the van that was making the sound, right? And the second one that we watched, it would be the speed of the fire truck coming towards us or away from us, because it was the fire truck that was the source of the sound. And of course, the units for that are going to be meters per second. VW would stand for what? Speed of the wave, which is usually going to be sound. Certainly in the two videos that I just showed you, illustrating the Doppler effect, it would be sound, because the sound from the horn is the wave was the sound, and the sound from the fire siren. I'm not going to call it the speed of sound. I'm going to call it the speed of the wave. But 9 times out of 10, it will be sound. And it's going to be measured in meters per second as well. Now, the only other thing here that we got to watch for is this. This is the first time we've ever seen this. And it's funny because it's the last equation that we do in Physics 20, plus, minus. Well, it's never both. I'll tell you, when you're solving one of these questions, it's either going to be plus or it's going to be minus, not both. When is it plus? When is it minus? Go ahead. So you're saying it's plus when the source is coming towards us, and it's minus when the source is going away from us. No, backwards. That's okay. Honestly, I've told you guys before. In fact, there was a situation like this just the other day where we were talking about diffraction and interference, right? And I remember I said, I never remember whether it's low frequency or high frequency that diffracts more. I have to think of that story of me trying to listen to my AM radio show at the bottom of the hill in order to remember that. I got to figure this one out too. I never remember this either, plus or minus. I never remember this. So I can't expect you to remember it. I figure it out every time. I figure it out. Here's the deal. We know when a sound is coming towards us, it appears to be a higher pitch, right? So if the source is moving towards us, FD is going to be a big number. If it's going away from us, FD is going to be a small number. How do I get a big number for FD? Do I want a big number on the bottom or a small number on the bottom? Kelly? Small number. So to get a big number right here, I got to get a small number here. And if I get a small number here, how am I going to get it? By adding two numbers together or by subtracting? Subtracting, right? So we're going to make it negative if the source, if the source, not the source is, if source is moving towards the observer, and it's positive if moving away. I don't expect you to remember that because I don't remember that. This is the 22nd year I'm teaching Physics 20. The 22nd year I'm teaching the Doppler effect, and I don't remember whether it should be plus or it should be minus. I figure it out still every time. All right. This can be ugly rearranging, like big time ugly rearranging. The good news is I'm only going to give you questions where you have to solve for either FD, the Doppler frequency, or FS. I won't ask you to solve for VW, the speed of the wave. It's ugly rearranging. If you think t is equal to 2 pi squared L over g was ugly, okay, this is worse, solving for VW or VS. So be prepared to rearrange it to solve for this or to solve for this. Okay? In either case, this one is already done. If you're solving for FS, what would you do? Just divide by everything, right? It would be FD over bracket VW over VW plus or minus VS. Okay, so that wouldn't be all that hard. All right, let's take a look at an example on page 432. All right, our last example of the year. And it's a pretty good one, actually. Requires us to do quite a bit. Good one to finish off with. Train is moving, it's traveling at a speed of 30 meters per second. Its whistle generates a sound wave with a frequency of 224 hertz. You're standing beside the train tracks as the train passes by you with its whistle blowing. What change in frequency do you detect for the pitch of the whistle as the train passes if the speed of sound in air is 330 meters per second? Well, firstly, we know that the pitch of the train whistle doesn't actually change, right? It just sounds like it changed. Sheldon, as we were watching the Big Bang Theory here a little while ago, said that the Doppler effect is the apparent change in frequency of a wave due to the relative motion of the source and the observer, not the real change. So it doesn't really change, it just seems like it changes. What do we have here? Clearly a Doppler effect question. We've got a speed of 30.0 meters per second. We've got something is 224 hertz. We've got something else is 330 meters per second. What are all these things? What's this 30 meters per second thing? The train is traveling at 30 meters per second. V what? VW or is it VS? Alex? Good, it's going to be VS. This 224 hertz, what is that? Frequency, right? FD or FS. The whistle generates a sound at the frequency of 224. The Doppler frequency or the frequency of the source? Frequency of the source, FS. What's this one going to be? 330. Alex? Sorry? Good. VW. I have never in my life seen a VW go 330 meters per second. Okay, but this VW, the speed of the wave, is 330 meters per second. What are we looking for? Well, we're kind of looking for the Doppler frequency, but not as a final answer, actually. We're looking for the change in perceived frequency. So we're actually looking for the Doppler frequency as it's coming towards us, and then the Doppler frequency as it's going away from us. And then what are we going to do with those two? Subtract them, right? So let's write down our equation here. FD is equal to VW over VW plus or minus VS times FS. Is that correct? As it's going towards us, do we make that a plus or a minus? Well, remember, FD has to be a big number as it's coming towards us. How do you get a big number? By making this number on the bottom bigger or small? Small. And we make it small, Danny, by doing what? By subtracting. So we're going to make it VW minus VS. Let's sub in our numbers here. 330 divided by 330 minus 30 times FS, which is 224. Let's pull out the calculator for this just to make sure that we can all do it here. When we do this, we end up getting 246.4 hertz. That's a reasonable number, right? When it's coming towards us, we should get a higher value. We perceive a higher frequency. The real frequency is 224. We perceived 246. It seems reasonable. Now let's look at when it's going away from us. It's past us. It's traveling away from us now. Now FD will be equal to VW over VW plus or minus VS. What's it going to be this time? It's going to be a plus. We want a smaller number for FD And if it's a smaller number, we have to have a bigger number on the bottom. And to get a bigger number, we're going to add those two values of V. So VW is 330 over 330 plus 30 times 224. Do the math on that one. We're going to get, what, 330 divided by 360 on the bottom there. Press equals, multiply that by 224. Gives me a value of 205.33. Does that seem reasonable? Yeah, I hope so. It's going away from us. We should have a lower pitch than it really is. The real pitch was 224. We perceive it to be 205. What's the apparent change in frequency? We're going to say it's 246. Technically, it should be final minus initial, right? 205.33 minus 246.4. And we end up getting negative 41.1. What's the apparent change in frequency? Well, it seems as if it goes down by 41.1 hertz. And that's why you hear what you hear when the fire truck or the train or whatever it is goes by you. You hear that instant it goes by you, it goes down, okay, very quickly from a higher frequency to a lower frequency. All right. Take a look at page 432, please.